Okay, let's go ahead and get started. Um, okay, so I wanted to say a few words about the midterm. So based on talking with a few of you, it sounds like it was maybe harder than expected, and I think a lot of people felt like it did not go the way that they wanted to. So I just wanted to say that it wasn't my intention to write a really hard midterm. And I know that like when you take an exam that is harder than you anticipated, that like it feels very stressful afterwards, and that can be like distressing. So I feel bad about that happening, and I'm sympathetic to like how you might be feeling about it. So as I'm grading it, I'm being really generous with partial credit and just trying to see in what you wrote, like that you've demonstrated that you understand the material, not necessarily that you reached a full or complete solution. And once I'm done grading them, I will sort of like look at the exams holistically and decide like if they need to be curved or like what happens with that going forward. So yeah, I just wanted to say some things to like reassure you all that it's not the end of the world that if you came out of Wednesday like feeling like things didn't go well. Are there questions? Okay, so, oh yeah, I guess also in terms of getting them back, there is someone who, because of some circumstances, is going to be taking the midterm Friday, like late afternoon. So I won't be able to hand them back until after spring break, which is like not ideal because that's like pretty far after you initially took them. I've gone back and forth on like if you want to have the grades posted once I have them ready, because like if you just see the grade and don't necessarily have the exam to look at, then like it's just a mystery number. But and also like I don't want to like have that like looming over you going into spring break or anything. So what do you all prefer? Do you want me to post the grades when I have them, or just like wait until after spring break to post the grades? Post them when I have them? Is that the, okay. All right, so, okay, so I will post the grades when I have them. And I'll also like post a comment at that time about like if they're gonna be curved or if there's gonna be like some opportunity to like rewrite answers or something like that. So yeah, that's what's happening with the midterms. Okay, so anything else? Okay, so with that, we are moving into a new topic, which is rings. I should put the date on this too. Okay, so up until now, we've been dealing with sets that had one operation, right? Groups, in a group, you only have one operation. But a lot of sets that you encounter in math naturally come with two operations, addition and multiplication. And when looking at certain things as groups, we've just been ignoring one operation at a time and not really worrying about how those operations might interact. So now we're going to introduce like an abstract algebraic structure that captures what's going on when you have two operations, and we're going to spend some time studying those things. So let me define rings. So a ring R is a non-empty set with two binary operations So the binary here just means that they take in two arguments. So you have like a plus b or a times b. So they just take in two things and produce another thing we'll call them addition. And times, which is multiplication. And they satisfy, so for all A, B, and C in our set, we have the following. So the first four axioms that I give you are going to be summarized as saying that this is a group under addition. So, and actually more than that, it's an abelian group under addition. Okay, so what are the first four axioms? We have that addition is associative. So A plus B followed by adding C. Is the same thing as A plus B plus C. Okay, addition is commutative. So A plus B is equal to B plus A. There's an additive identity. So there is and it's usually called zero. So the way that this works, of course, is that 0 plus anything is equal to that thing again. And then there are also additive inverses. So for all A in R, there exists something called minus A with A plus minus A equal to 0. Okay, so up to this point, hopefully it's all good because these are things that we've been dealing with all semester. So we're going to get two additional axioms that deal with the multiplication. So we have that multiplication is associative. So A times B, and then followed by multiplication by C is the same thing as first multiplying B and C, and then multiplying by A on the left. Okay, and then the last thing is that we have some distributivity laws. So this tells you how multiplication and addition interact with one another. So A times B plus C is equal to AB plus AC. And then there's like the right version of that. So if I do B plus C times A, that's equal to BA plus CA. Okay, so in summary, a ring R is an abelian group under addition. And times is associative. And distributivity holds. Okay, are there any questions so far? Okay, so let me just make some comments on what we're lacking. Okay, so we may have that multiplication is not commutative. Another thing that we do not have is we don't necessarily have a multiplicative identity. And we don't necessarily have multiplicative inverses. So what we're going to spend some time doing is exploring the consequences of not having these things, and also looking at the special cases when you do have them. Yeah, do you have a question? Yeah. Yeah. Maybe I'll add that. Okay, other questions? Okay, so going along with these observations about what might be missing for the multiplication, let me make some definitions. So if the ring is commutative under multiplication, then you just say that the ring is commutative. So if multiplication is commutative, we say that R is commutative. Okay, and this isn't ambiguous with the addition versus multiplication, because the addition is always commutative. So when you say that the ring is or is not commutative, that specifically refers to the multiplication. Okay, and if there is a multiplicative identity, so let's say if A is a multiplicative identity, then you call it a unity. And then the last bit of terminology is that a unit is an element of the ring with a multiplicative inverse. Okay, so I'm going to give you some time to think of possible examples of rings, and we'll make a list of examples. And with these, I want you to think of, are they commutative, and what are the units in the ring? Okay, what examples of rings do we have? What examples did you come up with? Do you have one? Yeah, okay, so that was also the first example I wrote down. So z with plus and times. Okay, so is it commutative? Does it have a unity? Yeah, what's the unity? 1. And then what are the units? Yeah. Yeah, so 1 and -1 are the units. Okay, these are the only things that that have multiplicative inverses, right? They're each their own multiplicative inverse, and anything else you'd need a fraction to invert it. So, okay, so that is a first example. What other examples did you all come up with? Yeah. Yeah, so let's just, n by n matrices over, let's just say R or C. Okay, so is this one commutative? I think no, right? Because matrix multiplication isn't commutative. And then, does it have a unity? Yes. Yeah, so I'll just call it I n by n. So the identity matrix is the unity. And then who are the units? So which matrices have multiplicative inverses? Yeah. Yeah, so they have to have determinant not equal to 0. So det not equal to 0 if and only if m is a unit. Okay, is it clear? Okay, other examples? Yeah.
All fields?
Yeah, fields. So you took 540, then you know what this means. If you didn't take 540, don't worry about it. But fields are rings, and they're commutative. They have unity, and anything that's not 0 is a unit. Other examples? So what about z mod n with addition and multiplication mod n? Is it a ring? Yeah. Seems like a ring. Is it commutative? Yeah, so this one is commutative. One, again, is the unity. It's hard to think of an example of a ring that doesn't have a unity. I didn't add one to this list. I should think of one. One is the unity. What are the units? Yeah. Yeah, so the units are all of those things in this set that are relatively prime to n. So you have another name for that set. which is UN, so relatively prime. Yeah, so if you're relatively prime to n, then you will be invertible under multiplication mod n. Okay, I had one other example that I wanted to mention. So the set of polynomials with your favorite set of coefficients is a ring. So we could take polynomials with real coefficients or complex coefficients or integer coefficients. So these are polynomials. Under addition and multiplication of polynomials, and this is a commutative ring with unity 1, and then the units are plus and minus 1. And I wanted to bring up this example because a lot, like a substantial portion of abstract algebra and ring theory in particular is devoted to studying polynomial rings. And part of why is because one of like the biggest advances of modern mathematics in like the last, I don't know, century is realizing that rings of polynomials correspond to geometric shapes, and so you can learn things about geometric shapes from studying the corresponding ring of polynomials. So this is like a huge source of examples of rings, and also like why I would say modern mathematicians like care at all about rings. This is polynomial rings. Okay, so I'll give you another definite, or were there other examples that people thought of that we want to talk about? Okay, I'll come up with one that doesn't have a unity and let you know. Okay, so here's a quick definition. So this is just the direct product for rings. So given rings R1 up to Rn, we can construct the direct product, which is written as R1 O plus up to Rn. And again, like similar to how this was defined for groups, this is just n tuples where the ith element comes from the ring R sub I. And addition and multiplication are done component-wise. Is it clear what I mean by that? So if you want to multiply two of these things, then you would just go into each entry and multiply the corresponding elements. Yeah.
Is this under the addition function or the multiplication function?
What do you mean? So this is like I'm constructing a set. Yeah. So this is like the set of n tuples where it comes from, the ith entry comes from the ring R sub I. And yeah, my claim is that this is a ring where you define the addition and multiplication operations component-wise. Okay, so let's get some properties about rings. So I'm gonna move to a new page, so get a proposition. So this is like some first properties of rings, just that we get from the hypotheses. So let's let A, B, and C be elements of a ring R. Then we get the following. So the first is that A times 0 is equal to 0, and also 0 times A is equal to 0. Okay, it seems pretty obvious, but we have to prove it from the axioms for a ring. The second one is that A times the additive inverse of B is equal to the additive inverse of A times B, which is equal to the additive inverse of AB. Okay, so all three of those things are equal to one another. The third property is that the additive inverse of A times the additive inverse of B is equal to AB. Then 4, if there is a unity 1, and so we'll just call the unity 1, then the additive inverse times the unity times the additive inverse of the unity times an element A is equal to the additive inverse of that element A. And then the last one is that if there is a unity called 1, then the additive inverse of 1 times the additive inverse of 1 is equal to 1. Okay, so I'm going to prove 1 and 2, and then I'll give you time to work on proving 3 through 5. So I think 1 and 2 are the trickiest, and then 3 through 5 sort of follow from 1 and 2. So let's go ahead and prove 1. And this is going to rely on properties that we already know about groups, because rings are an addition under groups. We can use things like cancellation law for addition, or uniqueness of additive inverses for addition. So let's start off by computing 0 plus A times 0. Okay, so since 0 is the additive identity, this is equal to A times 0. This is by additive identity. So then it's equal to A times 0. 0 is equal to 0 plus 0. So we could replace 0 that way. And then we can use distributivity. So I'm just going to scoot all these down again to get A0 plus A0. So this is by distributivity. And now from this equality, we get that 0 is equal to A times 0 by the cancellation law for addition. because addition is a group. Okay, so I can cancel off these two a times zeros. Okay, and so then that establishes this equality, the first one, and the second one would follow completely analogously. Okay, are there questions about that proof before we move on to the second one? Okay, so for 2, I'm going to start this by doing a calculation. So we want to show basically that this thing, whatever it is, that it is the additive inverse of AB. And I know that additive inverses are unique. So what I'm going to do is add this thing to AB and see if I get 0. Because that will tell me that it's the additive inverse of AB. So we'll do A times negative B plus AB. Okay, so we can use the distributivity law in reverse. So we get A times negative B plus B. So this is distributivity. And then B plus minus B, of course, is 0. So we get A times 0. So that's because this is the additive inverses. And then A times 0 by part 1 is equal to 0. Okay, so for groups, which addition here is a group, we have that additive inverses are unique. So we know that A times minus B is the additive inverse of AB. So that tells me that A times minus B is equal to minus AB. Okay, and the other equality would follow in a proof similar to this. Are there questions? Okay, so I'm going to give you a few minutes to think about how to prove 3 through 5. And I think of these, so they all kind of use 1 and 2, but of these, 4 and 5 are the easiest and 3 is a little bit more tricky. So I'll give you a few minutes to think about those. And then I'll just finish up with some last comments about rings. Okay, I'm gonna give you one more property about rings. So this says that if you have a unity, then the unity is unique, and also if an element has a multiplicative inverse, then the multiplicative inverse is unique. So let's let R be a ring. So first, if R has a unit, a unity, so that's a multiplicative identity. Then it is unique. And second, if an element A in R is a unit, then its multiplicative inverse is unique. Okay, I'm not gonna reprove this because it follows almost exactly the same as the corresponding statement for groups did. But if you want to work through this, it's a good exercise. And then I just wanted to mention one more thing about rings. So this is a caution. So in rings, we don't have cancellation laws necessarily. So if you have that AB is equal to AC, that does not imply that B is equal to C. So this can fail to be true in a ring. And on Friday, we're going to look at a special type of ring where you do have cancellation laws. So Friday, we'll look at something called integral domains. Where you do have cancellation. Okay, so I'm gonna stop there for today. Are there questions about anything? Yeah. Yes, you do still have cancellation laws for addition because addition is a group and you have the group cancellation law. Yeah. Okay, then I'll see you on Friday. Hey, Bob. Yeah, because you basically don't need multiplication to satisfy anything. It just has to exist. I mean, obviously it has to satisfy these two things, but those are very mild asks. Yeah. Okay. Yeah. So even numbers. Yeah, it's even numbers. Yeah, that was the other guy had the same question. Yeah.
I hope you have a good spring break.
Oh, thanks, you too.
I think we could all use it.
I really like rock climbing, and unfortunately, the weather does not look that good for it. I was like hoping that it would be dry, but it looks like it's gonna be raining the whole time. So
Yeah.
I might just take the chance to like get ahead of work so that
Is there an indoor place that you can?
Oh yeah.
Yeah.
There's indoor places.
It's not the same, but.
One of these days I'm gonna come in early and just join your abstract algebra class.
I'm okay. How are you?
Are you taking a math class this semester?
I'm taking graph theory.
Oh, nice.
Yeah. What are you teaching next semester?
Teaching 540 with the alternate.
My voices tell me, be still, have faith, stay clear of the rat race. It's alright, simple like the flowers, and just love. Worry not about tomorrow. Be simple like the flower. Come smoke my word. Make your heart like an ocean, mind like a clear blue sky. Come smoke my word. Make your heart like an ocean, mind like a clear blue sky. Come smoke my word. Do you believe creation desires your devotion through murder and death? Squabble over pieces of the earth. The true beast are those who believe in creation without mother, womb, or birth. Be simple like the flowers. Come smoke my earth. Make your heart like an ocean, mind like a clear blue sky. Come smoke my earth. Make your heart like an ocean, mind like a clear blue sky. Come smoke my